Hello, thank you for coming to my talk. I'm Andrew Davis. I'm part of the Advanced Computing Programme here at UKAEA, and I'd like to talk to you about what I've been using the ARM Catalyst system in UK4. So first of all, I'll give you some background into who we are. UKAEA, the United Kingdom Atomic Energy Authority, is the UK's national fusion laboratory. We host the Joint European Torus, the world's largest tokamak, and we also host the UK's Massed Upgrade Experiment, which is looking at the benefits of compact spherical tokamaks. Our overall mission is to deliver sustainable fusion energy and maximise its scientific and economic impact. Fusion is the act of joining two light nuclides and creating a single heavier one. The difference in mass between the start and the end states releases energy. The most convenient method that we currently have is to take a gas of deuterium and tritium, which are two heavy isotopes of hydrogen, and heat this gas until its electrons are stripped, making it a plasma. The interaction rates between the gases are highest at around 150 million degrees Kelvin, which is 10 times hotter than the core of the Sun, and all we have to do really is keep the plasma hot and we're all done. However, reality, when the plasma collides with the walls around the device, it cools, and so we must keep the plasma insulated from the wall, and we do so using magnetic fields. So we must provide a number of fields, some which provide confinement and some which provide control. Here's an example of the Compass tokamak in Prague. If you notice the time scale in milliseconds in the top right hand corner of the video, and you'll see we have some dust and dirt, the kind of bright spark floaters that come by. The most notable part here is that the coolest part of the plasma is that glows brightest. I've just played for a little while because it's quite pretty. Down at the bottom of the device you can see here we have the diverter, and you're seeing some these sort of photon torpedo-y things. They are the bits of dirt and dust that's being liberated. So what does a tokamak look like? This is a cross-section of what a tokamak looks like. This is the UK's Massed Upgrade Tokamak, which incidentally had its first plasma on Thursday. But the principles are the same nonetheless. There are a number of poloidal field coils around the device. These provide shaping and control. We have the toroidal field coils, which go around the device. They provide confinement and drive current. And right at the bottom down here we have the diverter. And one of the most important things is the vacuum vessel, which sits around the outside, and this keeps the atmosphere out. In terms of modelling, we have quite the challenge. The magnet systems push the plasma, and the plasma itself pushes back. Coil currents upwards of 70 megaamps, forces upwards of half a giganewton, combined with temperatures near the first wall of upwards of 4,000 Kelvin, and then mere tens of centimeters or meters away from the plasma we have 4 Kelvin superconducting magnets. So we have quite an extreme temperature gradient, going from 150 million degrees Kelvin in the core of the plasma to 4,000 Kelvin at the edge, and then down to 4 Kelvin in the magnets. The computational challenge here is you have to deal with this all at the same time. And certain things can happen so quickly where some of the models that we're used to applying no longer apply. We have a number of things we have to do. So to compound matters, we obviously want to keep things cool. You want things melting. We therefore have to model the cooling fluids, which are typically high pressure steam or water, but sometimes this of course could be a gaseous coolant like CO2 or helium. However, sometimes we would like to employ liquid metal cooling, which is interesting for a number of reasons, but comes with an additional modelling challenge in that it's subject to magnetohydrodynamics, which increases the computational burden from just purely simulating a traditional fluid. We also have to worry about the electrical impact there too. And of course, you also can have sometimes turbulent flows, but not always, and that it manifests itself as fluid structure interaction in the blankets. The plasma itself emits charged particles, which are source terms for heat. These can be distributed or quite peaky, like in the diverter, where we have heat loads of between 5 and 20 megawatts per meter squared. which can provide is a challenge from the cooling side of things, but in terms of the simulation side of things, any rapid transients here will have impacts downstream. Of course, the byproduct of the fusion reaction itself is a charged alpha particle, which is retained in the plasma core, but the uncharged neutron escapes and creates radiation damage. It also deposits heat and undergoes subsequent nuclear reactions, which further increase the heat load. This background is to give you an idea of the different things we have to deal with when performing simulations for fusion, and the computational challenges within. To further frame that, we can look at the fusion timelines. So in between now and 2040, there are a number of demonstration type plants coming online. So for example, ITER will have its first plasma fairly soon, 2027 or so. It won't, however, have its first DT plasma, which is where we'd see the combined effect of the different loads plus lots of neutrons until sometime around 2037. There are other interesting ones, of course, coming online, Spark, CFETR in China, and there will be a number of limited test facilities. So IFMIF is a test facility that will be built in Spain. There are some non-nuclear test facilities, so at UKAEA we will have the Chimera facility. But this is just to give you an idea of the range of devices and the range of timelines which we have in mind. Now, in between now and 2040, there will only be 3 years of DT operations at ITER where we can learn any lessons regarding neutrons there and then. Closer is the CFS device, the Commonwealth Fusion Systems device Spark, which hopefully will run relatively soon in the next 5 to 6 years for DT plasmas, and they'll have 10-second pulses. But the question is, from UKAEA's perspective, will we have access? But any fusion device planning to go big in the next sort of 20, 30 years will need to gain, to qualify and gain regulatory confidence and compliance in the absence of all the experimental data you might actually like to have. So there'll be a lot of cross-validation that will be needed, a lot of uncertainty quantification, and therefore small efficient testing will be needed. Here's an example of some the impact of the uncertainty of the nuclear data on the neutron spectrum, and here the point is that the uncertainty from that nuclear data doesn't always handle all the uncertainty you would need for that experiment to match exactly. So to try and fill the gap, we're going to have to leverage large-scale multiphysics. So if you want to simulate complete systems, we're going to need to do this on complex geometries, and we're going to have to worry about different kinds of analysis. So computational solid mechanics, computational chemistry, electromagnetics, fluid dynamics, radiation transport, microstructure heat transfer, and most importantly, it must scale to hundreds of thousands of cores, to the current generation of hardware, because if we truly need to simulate things as they are, that necessarily implies a geometric complexity which heretofore we have not been aiming at. And I think importantly, we must also be exascale gazing. So we must have a view of looking at the exascale. Now the code itself may not already be exascale ready, but there should be a long-term plan in how we'd be able to leverage the whole platform. So this would enable us to have multiphysics driven design. So here's an example of this is a real component that's being X-ray radiographed, and the subsequent simulation. So from this image we've generated a tetrahedral mesh which describes the real component, and then we are doing the subsequent FEA calculations on that component. So we're trying to get towards as-built geometries. This is a real component. We've also been looking at the impact of flow in diverters, and then how much the turbulence really matters for some of the components. And also we've been looking at some real systems that we have today. This is a component that is designed to absorb very high heat loads and transfer that effectively into a cooling fluid. All these simulations, I'm only showing part of them, were all performed at the ARM Catalyst system at the University of Leicester. So UKAEA is a relatively compute-hungry organisation. We have our own modest internal computational infrastructure, but we do bid into external pots and calls when they arrive, such as Archer in the UK, Prace in Europe, and so on. However, a big supplier currently to us is the Dirac Compute Service. it was through DRAC we first found out about the ARM catalyst system, and then through our colleagues at the University of Leicester we've been accessing into Catalyst UK. So as part of that multiphysics workflow that I mentioned, one of the key parts is radiation transport, where you need to follow exactly where the neutrons and photons created by the plasma go and what they do. And of course, those neutrons breed tritium, deposit heat, and drive secondary nuclear reactions. And importantly, with this, we must model the geometric complexity of the reactor, since its nuclear field is sensitive to small geometric details. For this work, we chose the open source Monte Carlo code OpenMC due to its good history of scalability. Historically and generally, Monte Carlo codes scale very well. If they're designed well, they can be embarrassingly parallel. And typically, in the modern world, we deploy a mixture of MPI and OpenMP to improve memory efficiency. So when we want to scale to bigger problems, if we're using pure MPI tasks, there'll be a lot of duplication of memory. And therefore, of course, OpenMC's threading performance on the Thunder X2 was of interest to us, particularly the benefits of SMT 2 and 4 if they were going to be really performant and giving us, good thread performance. For these tests, we used the stock GCC 8.2 compilers that were already present on the system. So we looked at two different thread bounding options, close and spread. However, we always bound to cores. So the idea here is that we ran on the SMT 1, 2 and 4 queue, we ran only 64 threads just to see what would happen. Even though knowing, of course, they were underutilized, that of course you wouldn't do this in real life, but this is testing just to see what's going on. What we do see here is that for the SMT 1, 2 and 4 with the spread configuration, we see good performance. This is what we'd like to see. This was not what we'd ideally see. We lose performance when set on the close mode, but again, this is not necessarily reflective of real life. But it was nonetheless interesting. For the sake of completeness, we extended this out to 128 and then subsequently 256 threads. In this view, we see up to 128 threads. So even on the SMT4 configurations, obviously we're underutilizing again. For the spread option, which is this one here, we saw reasonable performance after a massive hit when you break over into the second CPU. But overall, a really good speed up. We see a 90 times speed up basically for 128 SMT threads, which is really decent for us. Proc bind close didn't see quite the same, but overall the SMT2 did. However, this will become clear later on, I think, on the next slide. But the 4-way overall with close was quite poor. So this is the same view but extended out to 256 threads, and again we see a very similar speed up number to SMT2. So overall we found that the SMT4 was not necessarily worth it, but the SMT2 for us definitely was. In conclusion, OMP proc bind spread is really good for application, and I would say if we had one of these systems locally, I would certainly want to configure in the SMT2 configuration. This gives us almost 90 times speed up. And personally, I look forward to seeing the next generation of chips and seeing where this goes. And if we can start having core counts of 256 cores on a CPU, each with 4 threads, that would be really, really good. So again, thanks to DRAC and the team at the University of Leicester for giving us access and for keeping it running for us. If you have any questions, please feel free to email me at that address. Thank you.